Hi, and welcome to SkillCheck number 3, Chapter 5, the normal distribution. So in the first scenario, we're imagining that a company manufactures bolts and that the diameter of a bolt should be 12 millimeters. Of course, the manufacturing process is not exact, and so there is some variation. And so we can suppose that the bolt diameters are known to be normally distributed with a mean of 12 millimeters, but with also a standard deviation of 0.05. So there's some variation in the diameter of the bolts. And so in symbols, we write what we can see here in symbols, and that's going to be our model for the population of bolts manufactured. So based on this model, we can make some predictions. So in the first case, supposing that bolts that are more than 12.8 millimeters in diameter are too big, it must be thrown out. Then what proportion of bolts then, assuming the normal model is true, what proportion of bolts must be thrown out? So here's a picture of our model. We're looking at bolts that are more than 12.08 millimeters in diameter, and we need to know what proportion that is. Those are the ones that are too big. In order to get that proportion, we first need to know how many standard deviations separates the mean of our distribution and this value of interest, this 12.08. In order to determine that, we just need to standardize. So we take 12.08 minus the population mean divided by the population standard deviation, and we find that 12.08 millimeters is 1.60 standard deviations to the right of the mean of the distribution. So now that we've standardized, we're working with not the original normal model, but with a standard normal model, standard at 0 with a standard deviation of 1. So this now is the picture, and we want to know what the area is in the upper tail of this distribution. So we go to our Z table, and we look up 1.60, and we find that the area to the left of this Z score is 0.9452, meaning the area to the right of it is 1 minus that number. And so we can tell then that the area in the upper tail is 0.0548, and then therefore we can say that 5.48% of the bolts made will be too big and will have to be thrown out. Next question, suppose that bolts that are less than 11.92 millimeters in diameter are too small and must be thrown out. Again, assuming the normal model, let's predict what percent of bolts made are going to be too small. So in this case, we're looking at a lower tail. We still need to know the distance between 11.92 and 12 millimeters in terms of standard deviations. And then we need to calculate the area in that lower tail. That gives us the proportion of bolts manufactured that we predict that will be too small. So again, standardization, you take your value of interest, subtract the population mean, divide by the population standard deviation, and you see we get minus 1.60 this time. So in other words, 11.92 millimeters is 1.60 standard deviations to the left of the mean of this distribution. So recall that in the first question, we were at 1.60 to the right. Now we're at 1.60 to the left. We know the area in the upper tail is the same as the area in the lower tail in this case because of symmetry. And so we already know that the proportion of bolts that are too small is going to be 5.48%. Question 3, what proportion of bolts made would you predict to be within 0.08 millimeters of the standard of 12? That is, what proportion of bolts would you predict to have a diameter Y that's between 11.92 millimeters and 12.08 millimeters? So here's a picture. We're looking now for the area in between these two bounds. Now we've already did the calculations. We already know that the area in the upper and lower tail, each of those is 5.48%. And so that tells us that the area in between is 89.04%. And so using the normal model, we predict that the percentage of bolts within tolerance will be about 89%. Okay, let me take a little aside to talk about mathematical notation. Yeah, the two areas shaded in blue can be indicated like you see here, like this. What I mean is these two shaded areas here. What this symbol means is that we're talking about z-scores that are more than or greater than 1.6 standard deviations away from the mean in either direction, left or right. This symbol you see, the z with the two bars, that's called the absolute value. We can go the other way as well. We can use the same symbols to indicate the area between these two bounds. And so what these symbols here mean is that we're looking for z-scores that are less than 1.60 standard deviations away from the mean in either direction, left or right. That was the 89.04%. So again, a z with the two bars like this, that's called the absolute value. And its meaning is as I describe here. So just to say that once more, because this is something I want to make sure you know. In the first case, these symbols tell you that we're looking for z-scores that are more than 1.6 standard deviations away from the mean. And the next one is just indicating we're looking for z-scores that are less than 1.60 standard deviations away from the mean. So if you say more than, you're talking about the tails of the distribution. If you say less than, you're talking about the middle part of the distribution. Okay, so you're probably going to see that in the lab next week, assuming you're watching this video today, which is Tuesday, September 4th. Okay, so moving on to the last part of this skill check. Suppose you oversee the machines that make the bolts and that you can adjust the machines, you can tune the machines, let's say, so that you can change either the mean or the standard deviation or both of the manufacturing process. The question is, how might you change or how might you tune the machine to change one of these population parameters in such a way as to reduce the proportion of bolts that you have to throw out? And the answer is just this. You just need to reduce the variability in the manufacturing process. And how do you do that? You reduce the standard deviation. So the proportion of bolts that must be thrown out can be reduced by decreasing the population standard deviation of the manufacturing process. So here we have the current normal model for the manufacturing process. If we take this distribution and we reduce its standard deviation, this orange distribution is going to get skinnier and taller. So maybe something like this. And you can see the gray distribution, the area in those two tails is now smaller, which means the proportion of bolts you have to throw out is less than what it was before. Scenario number 2. Here we're pretending a farmer in PEI plans to grow russet Burbank potatoes that she hopes to sell to McDonald's. However, McDonald's will only buy potatoes that are more than 15 centimeters in length. So based on past harvests, the farmer estimates that the average length of her potatoes is 13.61 centimeters with a standard deviation of 1.34 centimeters. So she's going to use these values as a model for next harvest. And so the next harvest is assumed to follow a normal model with this mean and this standard deviation. And so we have a picture like this. It's a distribution centered at 13.61, and we're looking for potatoes that are more than 15 centimeters in length. So what proportion is that? Just like before, we need to standardize. So the standardization, again, always the same. We take our value of interest, this case it's 15, subtract the population mean, divide by the population standard deviation, we get 1.04, which means 15 centimeters is 1.04 standard deviations to the right of the mean of the assumed distribution for next year's harvest. So to make a picture, looks like this, and the blue shaded area in the upper tail, that's the proportion we're looking for. So we go, those are the ones that are big enough. So we go to the Z table, 1.04, we see that the area to the left of our Z score is 0.8508, so the area to the right is 1 minus that. The proportion of potatoes that are big enough then is 14.92%. Last question, if the next potato harvest yields 10,000 potatoes, How many of these would you predict to be too small to sell to McDonald's? Well, we know that the proportion that will be too small, according to our model, is 85.08%. And so we can go 10,000 potatoes multiplied by 0.8508. That gives us 8,508 potatoes. So we predict based on this model that about 8,500 of her potatoes will be too small to sell to McDonald's. Okay, and that's it. That's our skill check for this week. Let's see. Yep, I hope that was helpful. If you have any questions, you can put them in the comments, or of course, you can ask me in class. You can send me an email. That's all I need to say. So bye for now.